So we can proceed with the next presentation that will be given by Vladislav Vershinin from Moscow State University of Civil Engineering. And the title is Surface Breaking Cracks as a Prospective Method of Areal Protection from Seismic Rayleigh Waves.
The considered problem has arisen from an ultrasonic non-destructive testing. From researchers in that field, it is well known that elastic waves scatter at cracks. So an idea is to use surface breaking cracks as a barrier for seismic Rayleigh waves. The problem formulation is the following. We have cracks of a certain depth normal to the free surface of a homogeneous linearly elastic isotropic half plane. A harmonic concentrated load acting on the free surface of the half plane has such duration that it generates only one wave of each type. One longitudinal wave, one vertically polarized shear wave, and one Rayleigh wave. Cracks and monitoring points are located far enough from the loading point so that bulk waves significantly attenuate when approaching them, and only the Rayleigh wave retains high enough magnitude. Location of monitoring points are set to ensure similar attenuation of incident, reflected, and transmitted Rayleigh waves due to an artificial viscosity of an integration scheme. Here is an example of how a concept of areal seismic protection works. As you can see, at first, three types of elastic waves are generated, but bulk waves rapidly attenuate. When the Rayleigh wave arrives at the crack, it is partially reflected, partially transmitted, and some fraction of its energy is radiated into the solid via bulk waves. Please put your attention onto the magnitudes of the incident, the reflected, and the transmitted Rayleigh waves. You can see that they are pretty of the same order. It means that Rayleigh waves reflected from a barrier interfere with continuing to arrive incident waves, thus causing significantly higher seismic loads outside the barrier. It is evident that we must quantify waves reflection and transmission to determine optimal number of cracks and their parameters. In this figure, results of finite element analysis are compared with those obtained by Engel and Achenbach using a semi-analytical approach. They reduced the problem formulation for a single crack to two systems of singular integral equations of the first kind for dislocation densities across the crack faces. Then they solved these equations numerically and substituted resultant dislocation densities into appropriate representation integrals, thus obtaining displacement fields. Non-dimensional crack depth along the horizontal axis, magnitudes of the reflection and transmission coefficients along the vertical axis, calculated variables associated with horizontal displacements are depicted with solid lines, red solid line and blue solid line, and those variables related to vertical displacements are shown with the dashed lines. You can see that general quantitative agreement between the two approaches is rather good, yet this two considered approaches yield different constructive and destructive interference of Rayleigh waves. So it is still unclear which approach gives more accurate results, and it should be determined within a further research. Nevertheless, this general good agreement between the two approaches allows one to utilize the finite element method for quantification of effects of the problem parameters. In this slide, effects of the Poisson's ratio and the crack opening angle are analyzed. There are two possible approaches to crack definition. One can fix either a crack opening angle or a crack mouth width. This results in different ratios of the crack mouth width to either a Rayleigh wavelength or a crack depth. So these two cases have to be compared. It appears that the Poisson's ratio is responsible for the rate of the transmission coefficient decrease, as well as for a value range of the reflection coefficient and its magnitudes and locations of its local maxima. On the contrary, the way of crack definition affects only the magnitudes and the locations of the crack of the local maxima of the reflection coefficients. These quantitative effects, you can see in this slide, are of a moderate degree, and what is more important, no qualitative effects are observed. That's why one can quantify effects of other problem parameters using one particular value of the Poisson's ratio and one particular approach to crack definition. The next partial problem is to determine an optimal distance between two similar cracks acting as a seismic barrier. It has been determined that the transmission coefficient gradually decreases with the intercrack distance, and this is good. But at the same time, the reflection coefficient increases by up to 50%. This, in some sense, disappointing result indicates that a double crack is worse than a single one as a seismic barrier. And the natural question is whether there is any sense in constructing a periodic array of similar cracks. As it can be observed, the transmission coefficient has a local minimum when a periodic array consists of 5 similar cracks. Here it is. And the reflection coefficient has 2 local maxima when a number of cracks is 3 and 5. Unfortunately, both coefficients remain at the same order of magnitude under any reasonable number of cracks in the array. Hence, one may confidently conclude that there are no advantages of a periodic array of similar cracks over a single crack with regard to their seismic protection qualities. Finally, I would like to notice 2 directions of further research. The first one is to consider cracks filled with some dissipative material to reduce waves reflection and at the same time at least retain the transmission coefficient at the same level. And the second prospective concept is an array of cracks with different depth. Outer cracks with a small depth should yield low-level reflection of incident waves and prevent transmission of waves reflected from the inner crack with a large depth. and this large crack in its turn acts as a seismic barrier. So that's all the material I have prepared. I hope you have found it interesting. Your questions are welcome.
Yeah, thank you very much. Questions, please. I have a question. So can you reverse back to the slide where you were analyzing the effect of opening angle on transmission? So I'm not sure I understood what was going on there. Yeah, so can you once again explain what happens as we change the opening angle? Because I guess the main question here is if we will have contact between crack faces or not. Yeah, so if we consider crack as a mathematical cut, so the opening angle is 0, then for any compressive stress, we will just have contact, and that will be same if we have no crack. And as so soon we have tension, the crack will open and stop, well, not stop waves from propagating, but somehow interact with them. So it's what can we say from your material here? Since I'm not sure I understood.
I see a question. In both cases, an ideal crack was modeled. The difference is actually in the angle of crack face's inclination relative to the free surface. When you fix a crack opening angle, then the angle of inclination of crack faces are constant under different crack depth. But if you fix a crack mouth width, then when you simulate very small cracks, then angle of inclination of their faces will be something like 45 degrees or even 30 degrees. So it will look like a small pit. But when we go back to the case of fixed crack opening angle, for any crack depth, you will have an almost ideal crack when when there is no contact between its faces, but its crack opening is very small compared to its other dimensions.
Yeah, but if the crack opening is small, that so soon we have a rather large compressive stress, crack should close, or you are not, so what kind of condition do you have for contact between crack faces?
I have considered such stress levels which is insufficient to close the crack. Because
okay, so
we consider only elastic waves, so that's the reason of no contact stresses, no closure of the crack.
Okay, so maybe better then you should say not cracks, but I don't know, angular cuts or something. Because if we say cracks, so we suppose something with opening that is much smaller comparing to the crack length. Otherwise, they should be angular cut. Or
it may be called trenches, for example. Yet this idealization of a crack is only meaningful when concerning numerical simulations, because large angles of inclination will distort finite element mesh and may potentially give inaccurate results. In all other senses, as you can see from these figures, there is no difference between the two cases, whether you fix a crack opening angle or a crack mouth width. So in both cases, you will obtain pretty similar results.
Thank you. So do we have more questions? Okay, if there are no additional questions, then we should thank Vladislav